A mound is a simple-looking structure from the outside, but inside you'll find a complex relationship between heat and moisture. That relationship is affected by various external elements, some of which we'll examine over the next few minutes. Let's look first at moisture readings at Inga Lake, 75 kilometers northwest of Fort St. John. 7 moisture probes were placed in, under, and around the test mound. 3 probes were placed in the mound, 2.5 centimeters below the cap, at the top of the inverted humus layer, and at the interface between the existing and inverted humus. Probes 4 and 5 were placed in the mineral soil under the mound, 2.5 centimeters deep and 15 centimeters deep. Finally, probes 6 and 7 were placed in the ground, also at depths of 2.5 and 15 centimeters from the surface, but away from the mound. These control probes show normal site moisture. Readings were taken throughout the growing season. They show that the moisture level within the mound changes significantly, unlike the moisture in the ground. The chart at the lower left of the screen indicates moisture levels. Green is approximately 0.1 bars to 1.9 bars. Yellow is 2 to 5 bars. Orange is 6 to 14 bars. And red represents 15 bars and up. The upper right of the screen indicates the day and month. The following screens show the moisture levels found in, under, and around the mound between mid-May and mid-October 1995. As you can see, the moisture levels near the top of the mound are by far the most volatile. This graph represents the changes in moisture levels 2.5 centimeters from the mound's cap. The probe at the top of the inverted humus layer also shows volatility, although it is less affected by changes in moisture. The other 5 probes rarely exceed 0.3 bars, as the soil remains quite moist throughout the season. There's also evidence that orientation of the mound relative to the hole may also be important, particularly if the hole is filled with water. However, there's not enough data from this single trial to support that conclusion. Mounds react quite differently depending on how they're oriented. Different directions produce different readings, both for moisture and temperature. For instance, if the mound and hole are oriented north-south, the temperature and moisture levels differ from the mounds that are oriented east-west. Let's look now at temperature readings for 2 mounds at Inga Lake for one clear summer day, June 13, 1996. 4 temperature probes were placed within each test mound to measure how temperatures change during the day. The following screens clearly show the progression of peak temperatures found within each test mound. As you'll see, the temperature readings match the progress of the sun. The first mound has a north aspect. In other words, the hole is to the north of the mound. The sun's warming effect accumulates and travels through the mound. The morning sun begins to heat the southeast side of the mound first. Accordingly, probes 3 and 4, the 2 southernmost, register the highest temperature at the 10 a.m. reading. Air temperature, measured 15 centimeters above the mound, exceeds anything within the mound. At 2 p.m., the sun has been traveling from east to west across the southern face of the mound, and probes 3 and 4, which are furthest to the south, are several degrees higher than probes 1 and 2. All 4 temperature probes show much higher readings than at 10 a.m., rising between 5 and 9 degrees Celsius. And heat is accumulating in the mound. While the surrounding air temperature has risen 4 degrees, all the probes within the mound show increases of at least 5 degrees, and probes 3 and 4 register higher temperatures than the air. The heat continues to build within the mound faster than in the atmosphere around it. At 5 p.m., as the sun moves into the western sky, temperatures within the mound continue to rise. All the probes are 4 to 5 degrees higher than at the 2 o'clock reading, and as much as 13 degrees higher than the 10 a.m. reading. And despite the weakening sun, each of the probes is at least an hour from reaching its maximum reading for the day. Meanwhile, Air temperature rose only 6 degrees. All 4 probes now register temperatures near or above the surrounding air. This mound has an east aspect. In other words, the hole is to the east of the mound. Again, 4 probes are placed inside the mound, with number 1 closest to the hole, and number 4 being farthest from the hole and farthest west. The sun's warming effect accumulates and travels through the mound. Readings early in the day, at 10 a.m., show probe number 1 closest to the hole and to the rising sun in the east, with the highest temperature. Probes further away from the morning sun show lower temperatures at this time. The air temperature is higher than any point within the mound. At the 2 p.m. reading, as the sun has moved east to west in a southern arc, probe number 1 continues to record the highest temperature, as the east side of the mound was exposed to the sun all morning. However, as the sun has crossed into the western sky, probe number 4, the westernmost probe, records the second highest reading. All 4 probes show temperatures at least 5 degrees higher than at 10 a.m., while air temperature has risen only 4 degrees. By 5 p.m., probe number 4, the furthest west in the mound, is showing the highest temperature reading due to its extra exposure to the afternoon sun. The sun's southern arc from east to west is illustrated in the 3 other probes, which register temperatures in a very narrow range. Due to the accumulated heat in the mound, all 4 probes show a higher temperature than the surrounding air. As the heat continues to accumulate, it will be at least 3 more hours before the probes reach their daily maximum temperature. It's interesting to note that there's a significant range of temperatures found within mounds, from the top to the bottom, depending on time of day. Let's look at temperature readings again at Inga Lake, 75 kilometers northwest of Fort St. John. A total of 7 temperature probes were placed in, under, and around the test mound. 3 probes were placed in the mound itself, 2.5 centimeters below the cap, at the top of the inverted humus layer, and at the interface between the existing and inverted humus. Probes 4 and 5 were placed in the ground beneath the mound, 2.5 centimeters deep and 15 centimeters deep. Finally, probes 6 and 7 were placed in the ground, also at depths of 2.5 and 15 centimeters from the surface, but away from the mound. These control probes illustrate the temperatures normally seen in the ground at the site. The air temperature was also monitored for comparison. The chart at the left of the screen indicates temperature levels. Green represents a range from 16 to 22 degrees Celsius, an excellent growing temperature for white spruce. Pale green indicates 11 to 15 degrees, pale blue 6 to 10 degrees, and dark blue represents less than 5 degrees, a very poor growing environment. The information at the bottom of the screen shows the day and month. Readings were taken throughout the growing season. They show that the temperature within the mound varies significantly, and that unlike moisture readings, also change underneath the mound. As you can see, the temperatures near the top of the mound react most quickly to the sun's heat. So the uppermost probe, 2.5 centimeters from the mound's cap, reaches its peak temperature relatively early. It peaks at 3 p.m., while the probe 15 centimeters into the mineral soil doesn't peak until around midnight. The following screens show the temperatures found in, under, and around the mound on a series of clear, sunny days between mid-May and mid-October 1995. As you can see, the sun's warming effect accumulates and travels through the mound. Later, we see the heat has radiated down through the middle of the mound as well, and has begun to enter the ground underneath the mound. In fact, while the top of the mound reaches its peak temperature early in the day, the ground 15 centimeters beneath the mound doesn't reach its peak temperature until midnight, many hours later. That's how long it takes for the heat to radiate from the top of the mound down through the soil. As these screens show, the pattern of warming is repeated throughout the growing season. Note that the air temperature always peaks in the mid to late afternoon, unlike the peaks seen in the mound, which change with probe position and time of year. The relative warming power of the sun also plays a part, so temperature readings also vary according to month. The daily maximum temperatures are higher and reached later in the day in the early summer. As the summer progresses into fall, maximum temperatures tend to be lower and are reached earlier in the day. What this means is that earlier in the growing season, when the seedlings need warmth, they get it, because the mound warms much more quickly than the ground around it. It should also be noted that on overcast days, the differences in temperature are much less pronounced. It's apparent that although mounds seem simple, they are actually complex microenvironments. Further complicating matters is the relationship between temperature and moisture. Look at this compilation screen. It shows conditions on August 4, 1995 at the Inga Lake site northwest of Fort St. John. The temperature within the mound rises during the day as expected, and at 2 p.m. reaches an ideal growing temperature of 22 degrees at the top probe, 2.5 centimeters from the mound's cap. However, the moisture level near the top of the mound is at almost 17 bars, far too dry for the seedling. Both temperature and moisture levels have to be in the correct range for seedlings to flourish.